Then we have remote sensing for vegetation, classification, as well as in entertainment. That means what we want to conclude here is we are living in the world of images. Next, broadly we can classify image into three categories. Here we are talking about raster images, which can be classified into three types: RGB, grayscale, and then black and white. So this shows the RGB image, the corresponding grayscale image, and the corresponding black and white image. So RGB image, case of a binary image, it will be represented in the form of ones and zeros. Each pixel will be represented in terms of ones and zeros. So these are the three broad classification of images. Strictly speaking, it is a raster image. Resolution. So what is basically a resolution, the term? So resolution refers to smallest detail that can be seen with distinction. It is basically resolution. With respect to image processing, this resolution can be broadly classified into two types. One we call it as the spatial resolution, the other one we call it as the gray level resolution. So spatial resolution, and then we have gray level resolution. This slide indicates the spatial resolution variation. Spatial resolution is governed by the density of the pixel. So here I am showing two different images. So you can see that this image is represented by 3 megapixel. This image is represented by 1 gigapixel. As the density of the pixel increases, the clarity in the images is better. Next important thing is gray level resolution. We know that gray level is the value taken by the pixel. So gray level resolution depends on number of bits used to represent the image. Images with the different gray levels are shown in this diagram. If we allocate more number of bits, naturally the clarity will be better. Another terminology that is associated with respect to image is file format, in which form we want to store the data as well as retrieve the data. So different file formats that are commonly used are joint photographic expert group, tagged image file format, then portable network graphics, and then bitmap imaging. These are all the different types of file formats commonly used to store as well as to retrieve the images. The different areas of image processing we are going to summarize here. So if we take digital image processing, the area which is very common is image transform. Transform is basically used to represent the images in terms of the basis function. Different basis function gives rise to different transform. Then the next area is image enhancement. That is how to enhance the visual quality of the image that is given by means of image enhancement. Then we have image denoising. That is, if the images are corrupted during acquisition, storage, or transmission, how to overcome the impact of noise, or how to minimize the impact of noise, that is governed by image denoising. A closely related area is image restoration. Then you have another area called as compression. This deals with how to store the image effectively so that it can be efficiently transmitted from one place to another place. Then the next area in image processing is segmentation. Segmentation deals with partitioning of the image into different regions such that homogeneity is maintained within the region and heterogeneity is maintained across the region. How to do the processing of the image with respect to shape, it is governed by morphological image processing. Different techniques that are employed in morphological image processing are dilation, erosion, opening, closing, top hat transform, and so on. How to apply all these things to color image? There is a separate area called color image processing. All these things gives a 360-degree view of different areas of image processing. So image transform, enhancement, denoising, restoration, compression, segmentation, morphological image processing are few important areas of image processing. First, we will discuss with respect to transform. Transform is basically a representation of the signal. In this case, it is an image. The image is represented in terms of the basis function. Representation is through basis function. Different basis function gives rise to different transform. So the fundamental idea here is we want a representation. The representation is done through basis function. Different basis function gives rise to different transform. It is always not necessary that we are moving from spatial domain to frequency domain. Now, what are all the desirable properties that the transformation should address? The first important property that is desirable is generality. That is, the image transform should be in a position to represent wide classes of images. Next one is it should have very good energy compaction. That is, much of the information in the image should be represented by few transform coefficient. Then the transform is having good energy compaction. Then the transform should be able to adapt itself to different application, and then computationally efficient algorithm should be available to compute the transform. Then these are all the desirable properties of the transform. Now, what is the need for transform? That can be understood by a very simple slide. Here we can see that white light is falling on the prism and we are able to get Bezier at the other end of the prism. This phenomenon we call it as dispersion. If a person is standing on the left side of the prism, he will be able to see the light as white light. If the person is standing on the other end of the prism, he will be able to see white light as a combination of 7 colors. That means prism is giving this person to view white light as a combination of 7 colors. Similarly, transform is the tool which allows us to get additional information about the signal like frequency. So transform, it is basically a tool which allows us to extract information from the signal without disturbing the signal. Now, let us have an analogy in order to understand the basis function. So the analogy is with respect to people at one end, signal at another end. So we know that people belong to different classes, at least with respect to eating habit. We have vegetarian, non-vegetarian, lacto-vegetarian. Similarly, signals, we have different classes of signals like stationary signal, non-stationary signal, cyclostationary signal. The representative of the people happens to be, in India, it is MLA and MPs. The representative of the signal happens to be the basis function. So we are representing the signal through basis function. The people are represented through MLAs and then MPs. Here, group of this MLAs and MPs, they form the political party. Here, a bunch of basis function, we form the transform. That is, different basis function gives rise to different transform. So this is what we want to convey in this slide. Different basis function gives rise to different transforms. So one transform may not cater to wide category of signal. This is what we want to convey here. Next, classification. On what basis we can classify image transform into different categories? So if we take image transform, broadly we can classify into two categories, that is image independent transform and image dependent transform. Image independent means the transform basis function is independent of the statistics of the input data. Image dependent transform means the basis function depends on the statistics of the input data. So image independent transform we can broadly classify into three categories. One is sinusoidal, non-sinusoidal, and then multi-scale basis function. So sinusoidal transform, the commonly known transform is discrete Fourier transform. Then we have discrete cosine transform, and then Hartley transform. Non-sinusoidal, we have Walsh, Hadamard, and then slant transform. Multi-scale transform, we have wavelets and variants of wavelets like wavelet package, multi-wavelet, dual tree complex wavelet transform, contourlet, etc. If the transform basis function depends on the statistics of the input data, then it is an image dependent transform. Examples are KL transform and singular value decomposition. These are all the broad classification of image transform. So one of the powerful transform is Fourier transform. It was given by John Baptist Joseph Fourier in the year 1809. Actually, it was used to study the flow of heat through the object. See, in the Fourier transform, this is the thing we want to convey. That is, if we have a one-dimensional signal x of n, if I take Fourier transform of this dimensional signal x of n, we will be able to get the spectrum x of k. So x of k is the spectrum corresponding to x of n. If we have a two-dimensional function, it is represented by m comma n. M and n represents the spatial index. If we take two-dimensional Fourier transform, we will be able to get the spectrum as f of k comma n. Now, the expression for one-dimensional forward Fourier transform is given like this. In this e power minus j 2 pi by n kn, it is a complex exponential that forms the basis of Fourier transform. This basis function has both time index as well as the frequency index. That means it acts as a bridge between time domain and frequency domain. So in the case of two-dimensional transform, you have two-dimensional function, hence it is a function of two independent variable m and n. That is the reason why we have two summations here followed by f of mn. Then we have complex exponential which forms the basis function of the Fourier transform. Here m corresponds to spatial index and then n corresponds to spatial index, k and l correspond to the frequency indices. So this is the expression for two-dimensional Fourier transform. Whenever we take Fourier transform, we will be able to get two important information. One is the magnitude information, the other one is the phase information. So what is the role of Fourier transform in images? I am going to give you only one role. We are not going to discuss the entire role of Fourier transform. So one simple application of Fourier transform which I would like to discuss here is how this Fourier transform can be used to detect the periodic noise in the images. Now consider this image. It is basically an X-ray image. If I take the Fourier transform, then this becomes me spectrum. On the other hand, if this image is corrupted by a periodic noise, that is a sinusoidal variation, you can see that there is a drastic difference between these two images. So this image is corrupted by periodic noise. If we observe the spectrum of this periodic noise, we will be able to get two additional peaks in addition to the original spectrum. One corresponds to the sine wave e power j omega, the other corresponds to e power minus j omega. We know very well that sine theta is equal to e power j theta minus e power minus j theta by 2j. That is the reason why we get two additional dots in other than the original spectrum. If we can minimize these dots, then the impact of this periodic noise will be minimized. That is shown here. So we can minimize the impact of periodic noise by just filtering out the spectrum of my input image. Now we will continue the discussion like this. So we have an image, the corresponding spectrum. Now the difference is here again we have a periodic noise, but the frequency is higher. So compared to the earlier case, here the frequency of the sinusoidal interference, it is high. The corresponding spectrum, you can see that the dots are dispersed. The two dots are slightly dispersed, or the distance is large when compared to the previous case. We know very well that whatever action we do in one domain, it will have an impact in the other domain. That means compression in one domain leads to expansion in the another domain. If we can remove these two intensities, then the impact of this periodic noise, it could be minimized. So one application what we have discussed here is how this Fourier transform can be used to identify the periodic interference or the sinusoidal interference in a digital image. But this Fourier transform has some drawback. So one is it is complex in nature, but most of the images are real in nature. So there are different transforms are there in the case of images. One is Walsh and Hadamard transform. Then we have discrete cosine transform, which is purely a real transform. And then wavelet transform, which is basically a multi-scale analysis. Now, what is basically discrete cosine transform? Discrete cosine transform, it is a symmetrical extension of the Fourier transform. Here, this transform was developed by Ahmed, Rao, and then Natarajan. So, the picture of Ahmed Rao and Natarajan is shown here. With the due respect of these three personalities, the discrete cosine transform was developed by these three personalities, that is Ahmad, Rao and then Natarajan. The attractive feature of this discrete cosine transform is we know very well that cosine function is a even function. Cos of minus theta is equal to cos theta, and the DCT coefficients are all real, and then it has got very good energy compaction. Because of very good energy compaction, this discrete cosine transform, it was widely used in JPEG standard. So JPEG standard implied discrete cosine transform. If one is interested in time frequency representation, because Fourier transform is a very good tool which gives the frequency content in the image. If one is in need of both time as well as frequency representation, then the choice would be short time Fourier transform, which is known as windowed Fourier transform. The one-dimensional short time Fourier transform expression is given here. That is, we are having the signal, we are passing the signal through a window, and then we are taking the Fourier transform of the windowed sequence. Hence, it is called as windowed Fourier transform. Then the inverse expression is this. Then spectrogram refers to square magnitude of short time Fourier transform of the signal. Another powerful transform is a wavelet transform, because short time Fourier transform multi-resolution analysis is not possible. To get multi-resolution analysis, people developed wavelet transform. Originally, it was termed as ondelet. It is a French term which refers to oscillations of finite duration. Wavelets are basically oscillation of finite duration. It has to satisfy certain condition. If psi of t is used to denote wavelet, then the first condition that psi of t should satisfy is that the average value should be equal to 0, so that the function is oscillatory. Second thing, the energy should be finite. The third condition, it is commonly termed as admissibility condition, where psi of omega stands for Fourier transform of the signal psi of t. So if a wavelet satisfies all these conditions, then it is an eligible candidate to be called as wavelet. If a function satisfies all these three conditions, then it is an eligible candidate. The attractive feature of wavelet is multi-resolution analysis. That means we can represent the signal in different scales. See here, the same image, we can represent it in different scale. That idea, we call it as multi-resolution analysis. So multi-resolution analysis is the attractive feature of the wavelet transform. Next, it's an important area is enhancement. So what is the objective of enhancement? The main objective of enhancement is to improve the visual quality of the image. This is the ultimate objective of image enhancement. Our goal is to improve the visual quality so as to get a better perception of the image. It is a pre-processing technique. Mostly objective evaluation is available rather than subjective evaluation is available rather than the objective evaluation. That means there is no numerical value to say that this process is better than the other process. So subjective evaluation is commonly used for enhancement technique. So different types of enhancement technique I can broadly classify into two categories. One is in spatial domain, the other one is in transform domain. So broadly we can classify into spatial domain approach, frequency domain approach. In spatial domain approach, we have three categories. One is point operation, mask operation, and then global operation. Then point operation is normally termed as memoryless operation. Mask operation means with respect to group of pixels we are doing the mask operation. The mask size can be either 3 by 3, 5 by 5 or 7 by 7. So in mask operation, we have two broad categories. Either it is a linear or a non-linear filtering. Examples of linear filtering are averaging or low-pass filter or smoothing filter. Another opposite action is sharpening filter or high-pass filter. So non-linear filtering, classic examples are order statistics filter, which can be minimum filter, maximum filter, or median filter. So three different categories are shown here. Then point operation, simple example could be gray level transformation. Different types of gray level transformations are image negative, then thresholding, contrast stretching, clipping, and then we have thresholding. So identity operation, it is basically a simple gray level mapping. Here U represents the input image, V represents the output image, L represents the maximum gray level. We can observe that it is a straight line passing through the origin. It is of the form Y equal to mx. It is a straight line passing through the origin. So if we pass an image to an identity operation like this, we will be able to get the output image exactly same as the input image. So this device definitely now it performs like a voltage follower or a buffer. So output image is identical to the input image. Then classic example with respect to electronics is a buffer or a voltage follower. Then the next one is image negative. So image negative, this is the gray level transformation. U is the input image, V is the notation for the output image. If the input gray level is 0, output gray level is maximum. If the input gray level is maximum, output gray level is 0. It is called inversion or image negative. If I pass an image to such a transformation, output will be exactly like this. So this will be the output image. What we can observe is black turns out to be white and white turns out to be a black. So this we call it as image negative. Next gray level transformation, what we can observe is contrast stretching. So specific gray levels are enhanced in contrast stretching. So if this is the input image to this transformation, then we will be able to get the output like this. That is specific region of gray level, it will be enhanced. Now the next thing is clipping operation. So U represents the input gray level variation, V represents the output image gray level. So clipping refers to changing the contrast in this way. So input image is here and the output image is here. So this is what this clipping refers to. Another operation is basically thresholding operation. So see how thresholding operates. Here, this is the thresholding operation. You can see that input gray level is this, output gray level is this. Here, if the input gray level is less than 128, output will be 0. If it is greater than 128, output will be 1. That means it is able to convert a grayscale image into a binary image. Thresholding is an operation which helps to convert a gray level image to a binary image. This very well you can equate it to a comparator or a zero crossing detector in linear integrated circuits. Whenever you pass a sine wave to a zero crossing detector, the output will be a square wave. Now you see that sinusoidal variation, a small variation, you can see that it is the gray level. The output you can see that it is a binary image. It is called as logical operation. So people in computer science, they may be familiar with the term called logical operation. So here thresholding is basically a logical operation. The output will be either yes or no. So it is used to convert a grayscale image into a binary image. These are all the examples of enhancement which we want to highlight. This is the image before enhancement. After enhancing the contrast, you can see that the contrast being enhanced. Changing the contrast will give better visualization of the image. Now the next example is with respect to retinal image. If we pass this retinal image through an enhancement technique, we will be able to visualize the blood vessels in a better way. So visualization of the blood vessel helps us to understand whether some clotting is there on the blood vessel or not. So enhancement techniques are widely used to get better quality images. Next, we want to address image denoising. Whenever we want to address image denoising, we should know what are all the different types of noises that can creep into the image during acquisition, storage, or transmission. So different types of noises that are there in an image are additive noise, it could be multiplicative noise, impulse noise, or periodic noise. This impulse noise, again we can broadly classify into two categories. Either it could be salt and pepper noise or it could be a random value noise. Example for additive noise is AWGN, additive white Gaussian noise. Example of multiplicative noise is speckle noise. This speckle noise is very common in ultrasound as well as it is very common in SAR, that is synthetic aperture and radar images. Now, how we can minimize the impact of noise by means of these filters. Now, noises are similar to that of diseases and filters are similar to that of medicine. there is no one universal medicine which can cure all the diseases. That is the reason why we have wide varieties of medicines available. Similarly, there is no one filter which can filter out all the types of noises that are there in digital images. That is the reason why we have different classes of filters. This we can broadly classify into two categories: spatial domain filters and transform domain filters. In spatial domain filters, we have two broad classification. Either it could be a linear filter or it could be a non-linear filter. In linear filter, there are two. One is low pass, other one is high pass. So technically, it is given as averaging or difference filter. Non-linear filter classic examples are median filter, morphological filter, anisotropic diffusion filter. In transform domain, we have two different types of transform which I have already mentioned. That is, basis function depends on statistics of the data, or the basis function is independent of the statistics of the data. So a Fourier transform, DCT, wavelet all comes under the umbrella of data independent transform. So the basis function is independent of the statistics of the input image. Here we have PZA and IZA which are widely used for dimensionality reduction. So let us try to understand the salt and pepper noise, how it can be minimized using a median filter. So this shows an image of a cute baby which is being corrupted by salt and pepper noise. Here salt corresponds to white pixel and pepper corresponds to black dots. Salt corresponds to white dot, pepper corresponds to black dot. If I pass it through a median filter, then definitely the impact of the noise being minimized. How this median filter works, we will try to understand by a simple illustration. So here, this is the image that we have taken into consideration. So you can see that 1, 2, 3, 4, 5. So 5 by 5. Now, first we want to process this pixel means this is done by means of zero padding. So zero padding is the first thing we are doing it. There are different ways to handle the borders in the image. One such way is zero padding. Now what we do is we are taking a portion of the image. This we call it as the mask. Commonly preferred masks are 3 by 3 mask, 5 by 5 or 7 by 7, so that we will be able to get the mid value exactly. So for getting the mid value only, we are choosing odd value mask rather than even valued mask. So here we have chosen a 3 by 3 mask. So within this window, all these pixels are there. Now we are arranging it in the form of a column like this. The first operation in median filter is sorting of the pixel, either in the ascending order or in the descending order. So we have sorted it in the ascending order. The next important operation is finding the mid value, which is the median. So what we have done, we have chosen the portion of the image. We call it as the windowing. Within the window, the pixels are arranged in this way, and then we are sorting it, finding the mid value that is being replaced for this 78. So this action we call it as the median filtering. Now the mask will be moved over the image. See here, the mask which is moved over the image. Then next part will be taken, and then we are doing the same process, that is sorting and then finding the mid value so that it will be replaced by this. Now this part of the image is taken. So here the processing pixel is 255. So this 255 we are taking the median value. So median filter involves two operations. One is sorting, the other one is finding the mid value. Now this slide shows the impact of median filter. Now this is the original cameraman image which is being corrupted by 20% salt and pepper noise. This is noise density chosen is 20%. We have applied two different types of filters. One is 3 by 3 mask, the other one is 5 by 5 mask. 3 by 3 mask, the impact of noise is not that much minimized. But whereas here, the noise cleaning process is good, but we are paying a price to it. That means the edge information is lost. So how to retain the edge information as well as how to minimize the impact of noise, different variants of median filters are there in the literature that are given in this slide. One is weighted median filter, adaptive median filter, then decision-based filter, and then modified decision-based filter. These are all the different variants of the median filter. In this, we will try to address two important filters. One is weighted median and another one is adaptive median filter. So how weighted median filter works, we will try to understand it by a very simple illustration here. Here we have taken this as a image. Now the pixel to be processed is 55. Now we are taking this a 3 by 3 mask. Now this is the weight we are going to attach to this mask. We can very well observe that the center value of the weight is high, that is 3. And then it slowly decreases along the neighbor. So along the neighbor it is decreasing 2, and then towards the end it is going to be 1. It is almost similar to that of a Gaussian function. Gaussian function, you can see that the value diminishes along the edges. Here the value also slowly diminishes from the center pixel. What is the fundamental meaning of this weight is, this 76 will be taken 1, this 88 will be given a weightage of 2. So now we can very well understand the meaning of the weights here. So these are all the weights. That means 76 will occur only once, whereas 2 means this 88 will occur 2 times. This 55 I am giving the maximum weightage 3. You can observe that 55 is occurring 3 times. Now we are arranging this sorting. So array of elements, we are doing the sorting operation. That means arranging it either in the ascending order or in the descending order. Then the next process naturally is to find the median value, and then this 55 will be replaced by the median value, which is 85. This is the illustration for weighted median filter. Now the challenge is how to choose the weight. If you choose the weight like this, that is giving a maximum weightage to the center pixel and then giving minimum weightage to the surrounding pixel, you will be able to get some sort of a averaging, because we know very well that Gaussian function, they have the ability to perform smoothing action. So smoothing action can be enhanced by means of this weight. Proper choice of weight always it is decided by the application. Then the next variant of the median filter is adaptive median filter. So what is the fundamental idea behind adaptive median filter is, we want to change the size of the window based upon certain criteria. The criteria what is being fixed here is, we want to find whether the median of that pixel is between the minimum and maximum. If it is there, we are not going to change the window size. If it is not, then we are going to change the width of the window. So adaptive means based upon the condition. There is some flexibility is there. So what is the condition? The condition is this condition, and then if the processing pixel, it is not noisy, then it is retained as such. If it is noisy, then median value will be replaced by this P of I, X. This can be very well understood by taking a simple example. So now we are going for an illustration of the adaptive median filter. So this is the image that we have taken. So for this image, we are initially taking a 3 by 3 mask. This is the 3 by 3 mask, we have taken it. So we know very well that the minimum value here is 0, the maximum value is 255. Now we are computing the value which is called median value. So P of I, J represent the processing pixel. The minimum value, S mean corresponds to minimum value, which is 0. The maximum value, S mean it is 0. Median value is 255, and the maximum gray level what you can observe within this window is 255. So this terminology should be clear to you now. Pij refers to the processing pixel, which is what we are interested in. The minimum gray level is 0, the maximum gray level is 255. If we take the median of all these pixels, we find the value to be 255. Now we are checking the condition, whether the median is between maximum or minimum. So this condition, definitely it is not satisfied, because median value is equal to the maximum intensity value. Since this condition is not satisfied, we are just increasing the size of the window to 5 by 5 instead of 3 by 3. Now the processing pixel remains the same as 255. Now we are finding the minimum value, which is 0. Median value is now changed to 289, and the maximum value is 255. The condition is satisfied, so we don't have to increase the width of the window. But unfortunately, 255 happens to be a noisy pixel because it corresponds to salt noise. So this pixel has to be replaced by the median of its neighbors. So this, we can see that this pixel is being replaced by the median of value of its neighbors, which is equal to 89. So what we understand by means of median filter is there are different variants of the median filter that exist. Another area in image processing is compression. So we are going one area to the next area. So till now we have discussed enhancement followed by denoising. Then the next area in image processing is compression. So what is basically compression? Compression is basically compact representation. The objective of compression is to represent the data with minimum number of bits. Why we want to do it? Because of two important goals. One is effective storage, the other one is efficient transmission. So because of these two purposes, we are going for compression. One for effective storage and another for efficient transmission. So the need for compression, it can be understood by this simple diagram. So here what we have given here is different medical image modality starting from X-ray, CT, MRI. So for all this data, we need huge volume of data storage is required. So since we need huge volume of data to be stored, we are in need of some strategy to minimize the amount of data required for storage as well as further processing. So this can be understood by a very simple example. What is the fundamental philosophy behind compression? The fundamental philosophy behind compression is only one. That is, all the data will not convey useful information. So this data we can broadly classify into two types. One is useful data and another one is unwanted data. This unwanted data I can broadly classify into two types. One is irrelevant data, the other one is redundant data. So redundant is basically duplication, the other one is irrelevant. For example, going to an examination hall with more than one pen is basically redundancy. All of us might have appeared for an examination in our life. Mostly we won't go with one pen, we will go with more than one pen. That we call it as redundancy. One pen is sufficient to write the examination, but still we will go for more than one pen, hence it is redundancy. Redundancy is mainly for safety purpose. Then we have another thing called as irrelevant. What is basically irrelevant? So here you assume that I am the speaker, I am supposed to talk about compression. So what is compression, the need for compression, varieties of compression. Instead of that, if I speak about myself, that my name is Esakkirajan, my age is this, I am married or not, if I go on talk like this, then it is irrelevant. So it is not relevant in this platform, that is called irrelevant data. So how to minimize the irrelevant as well as redundant data, that is the challenging task in image compression. So here the idea is like this. We have useful information which is equal to data, and then I want to minimize these two so that I can get compression. So this can be understood by a very simple example. So here we can see that oranges. These oranges are difficult to transport from one place to another place. Now what we do is we are taking the essence of the orange. This is one way so as to minimize the size of the orange. The other way is to subtract the water content from this juice in order to convert it into a powder. This is what being done in the encoder side. At the decoder side, what we will do, we will take the powder, whatever is removed here, the same thing will be added here in order to get the orange back. So whatever we are doing it in day-to-day life, that somewhat resembles the phenomenon of compression. So here, how we can classify the redundant data in images. So different types of redundancy that is there in digital images are three types. One is spatial redundancy, another one is psychovisual redundancy, and the last one is coding redundancy. Spatial redundancy means the redundancy between two successive pixels, interpixel redundancy. It is the other name for spatial redundancy. The meaning is successive pixels in an image are almost alike. How to minimize that redundancy? It is done through transform. Psychovisual redundancy, it is basically, it deals with the limitation of the human visual system. Our human visual system will not respond to all the variations in the gray level. So if that idea is taken to minimize the redundancy, then we can minimize the psychovisual redundancy through quantization. There are different ways to code the data. One is through fixed length coding, the another one is variable length coding. commonly variable length codings are used to minimize the redundancy, that we call it as the coding redundancy. So this picture shows the difference between two different classes of compression. One we call it as lossless and the other one is lossy. See here we have original data. We are doing some compression in order to get the compressed bit stream. From the compressed bit stream, we are able to get the original data exactly, then it is called as lossless compression. From the compressed data, we are not able to get the original, but we are able to get an approximate form of the original. See here, this is an approximate form of this original, then it is called as lossy compression. So there are two wide classes of compression. One is lossless, the other one is lossy. For medical image compression, mostly lossless is preferred. So we will go for two examples. One which is lossless in nature, that is run length coding. So run stands for symbol, length stands for how many times it is occurring. Here we have dots. Along 12 dots are there in the row, 12 dots along the column. Each dot represent one pixel. That means 144 dots are there. If I am allotting one bit to represent one dot, then we are in need of 12 into 12. That means 144 bits to represent this pixel or this image. We are in need of 144 bits. Now how to minimize this 144 bits? That idea is run length coding. See here, this is 0. 0 has occurred for 12 times. The same thing is repeated here. So first value represents the gray level. The next one represents the number of times it is occurring. So this is the fundamental idea behind run length coding. To represent this 0, 1 bit, to represent 12, we are in need of 4 bits. So 5 bits are necessary here. So 5, 10, 15, 20, 25. Similarly here 25, so 50. To represent this, we are in need of 11 bits. To represent this, we are in need of 11. So 11 plus 11, 22. 22 plus 50, 72 bits. Instead of 144, we are in need of 72 bits, provided there is some repetition in my information. If there is some repetition in my signal, run length coding will give better result. If there is no repetition, then run length coding will not be a proper choice. Then next important aspect in image compression is transform based coding. So the steps involved in transform based coding are given here. First we have the input image. The input image is passed through a transform. The role of the transform is to decorrelate the relationship between the pixel. Then the second one is quantization. It is basically used to minimize the psychovisual redundancy, and entropy coding is to minimize the coding redundancy. In order to, if we do all this process, we will be able to get the compressed bit stream. From the compressed bit stream, we are doing the reverse process which is called as image decoding to get the reconstructed image. If the reconstructed image is exactly same as the original image, then it is called lossless coding, otherwise it is lossy. Whenever quantization is employed, naturally there will be some loss of information. In transform coding, what is the role of the transform? So these are the steps I have shown earlier. Then the role of the transform in transform coding is to decorrelate the relationship between the pixel and then to have very good energy compaction. So maximum information in the image should be packed into few transform coefficient that we call it as energy compaction, and then ideally KL transform has got very good energy compaction, but it is computationally intensive, so people they prefer DCT and Wavelet over KL transform. Next one is quantization. What is basically a quantization? Quantization is basically a many-to-one mapping process. It is not one-to-one mapping. It is a many-to-one mapping process. Hence, it is termed as approximation. Mapping large set of value to a smaller set of value, we call it as quantization. The best example is the grading system that is followed in countries. So, if one student is getting between 0 to 49, then F grade. Between 90 to 100, S grade. That means large set of value is mapped to a one set of value. Then we call it as the many-to-one mapping. From the grading, I may not be able to say clearly whether the score is 92 or 98 or 95 because all refers to same grade. It is called as quantization. So quantization is a non-linear process and it is a irreversible process. This quantization we can broadly classify into three different categories. These three different categories are scalar quantization, vector quantization, and then embedded quantization. So scalar quantization we can broadly classify into two types. One is uniform quantization, other one is non-uniform quantization. So grouping or approximating one particular value, we call it a scalar. Approximating group of values, we call it as vector. There are different varieties of vector quantization. One is we have TSVQ, tree structured vector quantization, multi-stage vector quantization, and then hierarchical vector quantization. Embedded quantization is widely used with respect to wavelet based coding. So in embedded quantization, we have EZW, that is embedded zero tree wavelet, then set partitioning in hierarchical trees, and then set partitioning in embedded block. These are all the different types of embedded coding scheme commonly preferred in wavelets which exhibits parent-child relationship. So if we can exploit parent-child relationship, then this type of quantization seems to be very effective to quantize the wavelet coefficients. So JPEG. So these are all the fundamental steps that are used in JPEG image standard, that is input image divided into blocks, that is 8 by 8 or 16 by 16 for computational efficiency. People are preferring either 8 by 8 or 16 by 16, and then they go for quantization, zigzag scanning, and then entropy coder. The reverse process is done in order to get the reconstructed image. Different types of JPEG modes are, we have sequential mode, either from left to right scanning or from top to bottom scanning. Then we have progressive mode, hierarchical mode, and then lossless mode. These are all the different types of JPEG modes available. The major drawback of this JPEG compression or decompression is the blocking artifact. Because of the partitioning of the image into 8 by 8 or 16 by 16 subblock, we have blocking artifact which is shown here. It is a visually annoying effect. So how to overcome that blocking artifact? People have started using wavelets. So it is JPEG 2000 standard. In JPEG 2000 standard, wavelet is widely used for compression. The fundamental philosophy in JPEG 2000 is compress once and decode many times. That means we have different scalability that is available in the case of JPEG 2000. It supports region of interest coding. It is widely used in medical image compression. Then it is less prone to error. The JPEG different steps followed in JPEG are forward wavelet transform, then quantization, then embedded block coding. We will be able to get the bit stream. From the bit stream, we are doing the inverse process in order to get the reconstructed image. The advantage of JPEG is that progressive transmission. So here you can see that we have only one time we have compressed and then we are decompressing many times. See here we are decompressing many times in order to get different spatial resolution. This is one advantage. Either we can do it in this way. The next one is with respect to position. Then the next one is with respect to components. Whether I'm in need of red component, blue component, like that. That is also possible. These are all the advantages of JPEG 2000 over JPEG standard. Legal wavelet is widely used in JPEG. So I think there is a question, which wavelets are used in JPEG scheme? So legal wavelets are widely used in compression. Whenever we choose a wavelet, definitely few criteria are important. It is desirable that it should be orthogonal. It is desirable that it should have been regular. Then number of moments, it should be minimum. So many criteria are there. It gives an overall view. Since I'm not discussing wavelet, I'm not getting into it. Now, the last section of this presentation is few applications of wavelet. So where we can apply this image processing. So image processing application, some of the application just I want to highlight. So one is with respect to agricultural field. In agricultural field, one of the important thing is fruit sorting and grading. We know that our nation is known for agriculture. So fruit sorting and grading. Here you can see that it is a mango. We want to know whether the mango being properly ripened or not ripened. So we have camera there. Camera is now used as the sensor. The feature can be color. If the color is green, then it is not ripened. If the color is orange, then the fruit is ripened, so that I can segregate the ripened mango from the unripened mango. It comes under the area of automation or machine vision. So here we are using the camera as a sensor. The beauty is it is a non-contact type of sensor. Now the next one is identification and classification of diseases in plant leaves. Here it shows the sorghum leaf. It has a healthy leaf. It is a disease relief. So how to use a machine learning approach to know that this is the disease that has occurred in the leaf and what is the solution that we can give for it. So it can be a very good application with respect to image processing. Then the rice grading. So rice grading, you can see that this is the machine which performs the rice grading. Rices will be poured from the top. Here these are all the cameras that are used here. So after grading, we will be able to see that we will be able to, this is the rice which is used for pouring. After grading, I will be able to segregate the unwanted things from this rice. So for rice grading, again the camera is used as a sensor. The knowledge is used as the algorithm. So we have to frame the algorithm in such a way that it works in real time in order to segregate the unwanted things from the rice. Next application with respect to image processing is with respect to medical field. In medical field, we have diabetic retinopathy. So in India, majority of the people, it is predicted that they have diabetes. Because of that, there will be some problem with respect to this vision, that we call it as the diabetic retinopathy. Here it shows the fundus images. So how to predict whether a person is prone to diabetic retinopathy or whether he is prone to other type of eye diseases based on either retinal imaging or OCT. Optical coherence tomography is also widely used to detect the glaucoma. Glaucoma and diabetic retinopathy are the most dangerous diseases which will lead to loss of vision. So these things can be well predicted by means of image processing and machine learning algorithms. Similar approach can be used for osteoarthritis, and then we can go for detection and classification of cancer tumor through mammogram image, and then fusion technology can be used to fuse the CT as well as MRI image in order to know the nature of the disease and the progressiveness of the disease. This is with respect to medical. Now with respect to security, basically for authentication, we are going for watermarking, hiding one image into the other, or steganography, cryptography, whatever we call like. Then another important area where image processing plays a role is automobile application. In automotive industry, night vision system plays a very, very important role. So how to drive in a foggy environment, especially whenever we are driving in a hill during the night time. So fog or mist will be a challenging problem. If our headlamp fails, how to know who is coming in the opposite side, that we know that it is a night vision system. So IR camera, whether we can build into this car so as to get a better view about the person who is coming in the opposite end. Naturally, the cost of the car increases. So how to minimize the cost and how to incorporate night vision system, it is an R&D performed in major automotive industries. Now, lane tracking, it is another important area, whether the car is deviating from the lane or not. So image processing plays a role where camera acts as the sensor. Then drowsiness detection, whether the driver is alert or he is going to sleep, we want to know. For that, image processing algorithms are widely used. Other than this automobile application, it can also be used in textile field. So in textiles, we have fabrics, whether is there any fault in the fabrics, how to identify the fault in the fabrics, that we call it as machine vision system in textiles. Then in geographical information system, that is for terrain classification, as well as to see whether the vegetation area is there or not. graphical information system. In this, radar images helps a lot. These are all the references. So the concepts are very well obtained from Gonzalez and Wood's book, which was published by Pearson. Some of the fundamental concepts being covered in our textbook, which was authored by Dr. S. Jayaraman, myself, and Dr. T. Veerakumar. Mathematical concepts can be obtained from Anil K. Jain, one of the classic book which deals with mathematical concepts of image processing. Computer vision related applications can be found in Milan K. Sonka textbook. An overall view about different areas of image processing, a holistic view one wants to obtain means Alan C. Bowick is a classic textbook. So these are all the references I have done, and this has been listed here. Now the session is open for discussion.
Thank you so much, sir. It was great to have the session from you. We have a few questions from our great attendees today. I will just read some of them out to you, sir, if you would like to take them. One we have is from Mr. Bibish Kumar KT. How to determine the mother wavelet of an image during wavelet transformation?
So it's a good question. So we have two things called as mother wavelet and then daughter wavelets. So daughter wavelets inherit the nature from mother wavelet. So daughter wavelets are merely dilated as well as the scaled version of the mother wavelet. How to choose the wavelet, that is really a challenging task that I have already mentioned during my talk. It should satisfy certain criteria. The wavelet should be whether it has to be orthogonal or bi-orthogonal, then how many moments it should have, then whether it has to be regular, whether some kind of asymmetricity has to be maintained or not. Because if symmetry is maintained, linear phase we will be able to achieve. So in some application, symmetry plays an important role because symmetry leads to linear phase. So if we don't want any phase distortion in our application, we want the wavelet to be symmetric. So these are all some of the criteria by which we can choose the wavelet. So always it depends on application.
So
I think I have answered the question.
Yes, sir. So are there any limitations as well of wavelet approach in terms of application? Asks Ms. Komal Asrani.
Everything has got its own strength and limitations. We know very well that designing a wavelet itself is a very, very challenging task. Very few people are involved in the design of wavelets. Dabachis is one among them. Then we have Mallat, Stephen Mallat. Then Professor Martin Wetterly. They have done exhaustive study on wavelets. So designing a wavelet itself, it's really a challenging task. So it requires a lot of time, energy, and in-depth idea in mathematics. So if we can design a wavelet by ourselves, then definitely it is a very good contribution to the field of image processing as well as signal processing.
Okay, sir. So
these
we
are
have
the
one
limitations.
more. Right, sir. So we have one more, sir. It says how to enhance an object in an image using pixel information.
So I have already mentioned there are two types of enhancement technique. One is in spatial domain, the other one is in frequency domain. So different techniques are available, starting from histogram equalization. We have adaptive histogram equalization, contrast limited adaptive histogram equalization, Retinex algorithm. These are all different techniques that are available in the literature to enhance the contrast of the image. All these things can be done in spatial domain. If we are interested, then we can go for frequency domain approach to enhancement. So these are all the standard techniques available in literature. One is histogram equalization, adaptive histogram equalization, contrast limited adaptive histogram equalization, and then we have, sometimes we can go for Retinex algorithm also to perform enhancement of the gray level. Sometimes people are using even morphological operators to get change in gray level.
Okay, sir. So we have one from Mr. Bipin Chandramandi. He says, mention please some examples of impulse noise.
Yeah, impulse noise, as I mentioned, it can be broadly classified into two types. One is salt and pepper noise, and another one is random valued impulse noise. Salt and pepper noise means image is corrupted by a gray level of 0 corresponds to black dot, gray level of 255, it corresponds to white dot. So during image acquisition, there is every possibility that image will be corrupted by random occurrences of zeros and 255 or during transmission. So that is the reason why people are very much interested in developing a strategy to handle the impact of the salt and pepper noise. So salt and pepper noise, as you can see my hair, the hair is a perfect example of salt and pepper. So it has got some black hair as well as there is some white hair. So random occurrences are there. So my hair is a perfect example of salt and pepper.
So there's one more from Mr. Manas Ranjan Mishra. He asks, is wavelet transform better than Fourier transform?
Definitely it cannot be said like this. So we cannot underestimate one transform and then we can say that other transform is always better than this transform. So Fourier transform, with due respect to Fourier transform, I can say that wavelet transform has got its advantages, definitely no doubt about it, but still Fourier transform has a role to play. I can even say that people haven't explored Fourier transform in depth. Still, lot of research is happening in Fourier transform. Fourier transform phase, how to interpret the phase of the Fourier transform, that itself is a challenging task. I think people have used the phase of the Fourier transform in face recognition. Lot of people, they have approached the phase of the Fourier transform as a tool for face recognition. So definitely we cannot underestimate any transform. We cannot say that wavelet transform is better than all the other transforms. So each transform has got its own strength and limitation.
Okay, so we'll take a few more questions in the next 2-3 minutes. We have one from Mr. Rajiv Ranjan. He asks, which tools, or can you please recommend the tool or software for image compression?
There are two things are there. Either we can go for a proprietary software or we can go for an open source. For proprietary software, we have MATLAB. Open source, we have Scilab, or we can do it in Python. Python is also now coming up in a very good way. So we can implement is computer CV. That is open CV is widely used. We can go for MATLAB, Scilab, open CV, or the algorithm can be implemented. If we are very good in C, then better to go for C or C++. In other words, we can go for Python. So it depends on in which programming language we are strong. Definitely we can get into it. This is one approach. The other approach is whether to go for a proprietary software or whether to go for an open source. If we are very much interested in open source, better to learn Python and then try to implement it in Python. If we are not bothered about open source or proprietary software, then MATLAB is a decent tool to implement the algorithm, understand the algorithm.
Okay, so we have one from Mr. Jeevan KM. He asks, is it possible to represent image pixels with other shape instead of square?
Pardon, I cannot get this question. Image pixel as a square.
So can it be represented in any other shape? Yeah, any other shape other than square. Representation of image pixels with any other shape instead of square.
Yeah, that's what he is talking. There are two things. One is called pixel, the other one is called voxel. So voxel is a three-dimensional representation or higher dimension, which is difficult to visualize. So two-dimensional, the better representation is seen to be a square. So it is only a representation, but what is more important is the images are represented in terms of numbers, that's all. It is an array of numbers. We are representing an image in a matrix, means we are representing it as an array of numbers which are arranged in two dimension. The better data structure that is available is a matrix. That is the reason why matrix is widely used as a data structure to represent the image.
Great, sir. We have one from Dr. Gomati Chandramohan. He asks, can you please explain the power spectrum of noise?
Power spectrum, actually we are taking the square magnitude of the Fourier transform that will result in the power spectrum. So in the power spectrum, purposefully I have chosen a periodic noise. So what is a periodic noise that is being added in my presentation is a sinusoidal periodic interference. We know very well that the formula for sin theta is e power j theta plus e power minus j theta by 2j. That means we can visualize sine wave as two phases which are rotating in the opposite direction. That is the reason why in my power spectrum, I will be able to get two dots other than my original power spectrum. The two dots correspond to one is e power j omega t, the other one is e power minus j omega t.
Great, sir. We have time for just one more, and this is the last question. How to identify the salt noise in an image which contains 255 as its original value in some pixels in the image?
Yeah, definitely it is a challenging task. If my border, so border can be image borders, naturally there will be an edge. So we should not misjudge the edge to be the noise. So that is the challenging task there. So in general, we are checking the pixel whether it is 0 or 255. If it is 0, then we are assigning it to a pepper noise. If it is 255, we are assigning it to a salt noise. If it is within an image, absolutely no issue. But how to handle the border, that is a challenging thing. So sometimes there is a possibility that we may misinterpret the edge information as the noise. So that we have to be a little bit careful. So I think the audience, they are very much concerned about the edges rather than the smoothness region in an image. So if there is an edge, we should not misinterpret the edge as a noise. That is really a challenging task.
Okay, so one of our attendees does really want to know, can we extend this knowledge towards video and sound signal processing?
Yes, video we know very well that it is a it is a signal. So if it is an image, normally it is a two-dimensional function f of xy. If it is a video, f of xy, lambda and t. That means lambda corresponds to the color and t represents to the temporal variable. So everything is a signal. Whether I am going to deal with one-dimensional signal, then it is DSP. If it is two-dimensional signal processing, it is image processing. Multi-dimensional signal processing, it is video processing. So whatever algorithm which works well for one-dimensional, definitely it should work well for images with slight modification. That's all.
Great, sir. I think this brings us to the end of the session.
I think I have one more question. Repeated. Sorry to interrupt, Prakriti.
Sure,
Mr. Abhishek Jain raised a very impressive question. How compressive sensing technique can be used along with DWT DCT? Please suggest the research paper. I think Mr. Abhishek Jain, Professor Richard Baronik, you can follow Professor Richard Baronik of Rice University. He has done excellent work with respect to compressive sensing. So you can simply Google in www.rice.edu. That means Rice University is the university in which lot of framework being done for compressive sensing. So compressive sensing, the fundamental idea is random sampling. So in compression, we are collecting the data and then we are doing the process to reduce the data. In compressive sensing, we are not collecting the data as such, we are collecting minimum data. That is the fundamental difference that comes under the idea of random sampling. So you can follow Richard Baronik of Rice University to get better clarity about compressive sensing. I have given overall view. That is the reason why I have not gone in depth about particular area. It's nice to know that some of them are interested in compressive sensing. So better to follow the work from Rice University. They have done lot of work related to compressive sensing. Even single pixel camera they have developed using compressive sensing. So compressive sensing plays a very, very important role because they are not collecting the entire data. They are collecting minimum data. From the minimum data, they want to extract the information. That is the fundamental idea in compressive sensing. Any other clarification to be done?
So I think they have a lot of questions. What I can do is I can take out all these relevant questions and mail them to you, and you can take them one by one.
Sure, we will do it, ma'am. So I wish to thank all the participants for patient listening, and I wish to thank Tata Mc Graw Hill for giving me an opportunity to interact with you all. So I wish to thank Prakriti also for making this session happen, webcast engineer, all of them who have worked to make this event happen. So I wish to thank the webcast engineer, Prakriti. I wish to thank all the officials in Mc Graw Hill, and last but not the least, I wish to thank the participants. So the success of the event depends on how the participants interact with the presenter. So all of them are very enthusiastic. I wish to thank them all for making this event happening.
Thank you so much, sir. That was a great interaction with all of the audience. Since we're at the end of the session, I would really thank you for this great session delivery, and I will also take this opportunity to thank all of our audience who brought in so much interaction to the session. And till even now, I can see that there are questions and praises for the session. So thank you, everyone. To answer one most common question, yes, the e-certificates.
One more thing I want to add. Sorry to interrupt.
Please, sir.
One more thing, I also wish to thank Mr. Navneet, who has taken a lot of effort. He has initiated this. So I take this opportunity to thank Mr. Navneet. It is because of his encouragement we have prepared the slides, and then we have modified the content. Frequent feedback he has given. I wish to thank Mr. Navneet, and then I wish to thank my teachers. That is Dr. S. Jayaraman, who is no more, and I wish to thank my colleague, Dr. T. Veerakumar, who have taken a lot of effort to prepare the slide. So it is not a one-man work, it is a teamwork. This is what I want to highlight. So it is a teamwork of Dr. S. Jayaraman, Dr. T. Veerakumar, myself, and my teachers. Thank you. I wish to thank all my teachers who sowed the seeds of digital image processing in my mind. Thank you. Thank you very much.
Thank you so much, sir. I think, in fact, we saw a comment from Dr. Veerakumar in our chat box as well. So I think we are very pleased to have him here with us today. Okay, so towards the end, I would just like to highlight, yes, to all the attendees, we will be sending out the certificates to you. You will receive them on your registered email ID within a day or so. Additionally, for all of you who have requested for sir's video, there will be the entire session recording, and it will be available soon on our YouTube channel, in which sir's delivery of the video as well as the presentation will be available. Any other queries, please do write to us at support.india@mheducation.com, and we will be more than happy to pass on your queries to the speaker, and whenever he gets some time, I think he'll be more than happy to respond to them. Thank you everybody for your participation. Be safe and have a good day. Thank you.
Thank you. Thank you very much.